That would be one way of writing that. If we take a look at a proof by resolution, let's say that these were given axioms. These are axioms after we converted them to clause form. I write my proof trees this way. This is, we're going to be looking across the axioms in clause form, and we're going to be looking for opportunities to eliminate propositions by looking at contradictory propositions. So in this expression, we have a single P, and we have not P or not Q or R. For both of these to be true, for this to be true and for this to be true, it must be the case that not Q or R is true, for the reasons we talked about earlier. And so I would combine these statements, resolve them, if you will. This would be a theorem. This follows from the known axioms, not Q or R, by canceling out or eliminating the references to P. I can take this theorem and I can resolve it with this theorem because I have a conflicting propositions, not Q and Q. This resolves to not W or R. Okay, not W from here, R from here. This is the another theorem that results from resolving these two statements. And then I've got this, and this resolves with W. Again, I have W and not W or R. For both of these statements to be true, it must be the case that R is true. Okay, so I conclude R. And I've shown R using, using resolution. Okay. It turns out that resolution all by itself is not complete either. We can take a look at this statement, and here I've got axioms that have been converted into clause form. And I want to prove P and Q or R. In this case, I can resolve statements. I can show P. I can resolve these two statements. I get S. I can resolve these two statements. I get P, S and not S or P. So I know P is true. I can resolve these two statements and I can get R. So I can show these by resolution, but to show Q or R, I need an additional operator, again, which is formally an inference operator in propositional logic called OR introduction. If I know R, I can disjoin that with any other expression involving some other proposition, and I know that's true too. Okay, so if R is true, I know Q or R is true. And that, through OR introduction, is the only way I can get that expression. I cannot get that expression with resolution all by itself. And then I can apply AND introduction to get P and Q or R. Okay, so I need additional resolution by itself is not solely sufficient to generate proofs. It doesn't work all by itself. But it turns out that resolution is sufficient, and the only inference rule you use when you do proof by, if you use proof by contradiction. And the way we're going to do proof by contradiction is we still have a set of axioms, and this procedure is summarized a couple steps back. You can look at it. This just points out that you can do proof by contradictions just with implication rules and whatnot. We can have axioms like this. We can conclude R. But in a proof by contradiction, what we would do is we would take, if we were interested in proving R, we would negate R, we would add it to the knowledge base, and then we would see, determine whether that generates a contradiction or not. So if I want to prove R by contradiction using just implication operators and modus ponens, as well as potentially some other operators, I would negate R, I would add it to the knowledge base, and then I would do these steps, and I would see whether R and not R both followed from the axioms plus the negated statement. So in this case, it does in fact add a contradiction to the database. If I can't find a contradiction, it means that if I add not R to the database and I can't demonstrate a contradiction, it means that there must be a model for the knowledge base that does include the possibility of not R. So I'm not introducing a contradiction. You can go back and look at that, but let me get to resolution. Here is the statement. Here is the statement we want to prove. What we would do is we would negate this. We would negate the expression we want to prove. We would convert it to clause form using the steps I've talked about earlier. These would be the two clauses of the, in clause form of the negation of the statement I want to prove. These both are then become part of the knowledge base that I can use in my proof. Turns out I don't have to use one of these. I can resolve not W or R with not P or not R. That would resolve to, R's would cancel, and that would resolve to this. I can resolve this expression with not S or P. The P's cancel. I get this expression. Not U or S resolves with not W or not S. The S's cancel. I get this expression. This resolves by with a single U. I get not W. This resolves with W. Not W resolves with W, and I get an empty set. And that's the sign of a contradiction in a resolution proof. Okay? Again, if there was no contradiction, if this had indeterminate value in the knowledge base that I was evaluating, I just keep searching for potentially forever. In this case, it would halt. In propositional logic, it would halt, but I would never find an overt contradiction like this. You don't really have to take this final step, but it is conventional to take it once you find this contradiction here. And you would just implement your theorem prover to look for the empty set as you resolve. Question here is there a simpler proof? This is a proof that, you know, I came up with by doing my own kind of search on the problem. We know that breadth first search is pretty good at finding minimal solutions, and we could use breadth first search in this case to look for a minimal length proof for a problem like this. So here's my axioms. Here's the negated sentence put into clause form. Again, I add that negated sentence to the set of axioms, and I simply search for all possible ways of pairing propositions, compound propositions here, in a way that will resolve or not make progress. You can create, depending on your implementation, I think a preferred implementation would only be looking at statements that actually resolved and reduced the statement length. So these two statements would certainly be resolved, and they would become a candidate because in this case the S's would cancel. But you can continue to do that in a breadth first manner at each level, not just resolving with the things at the same level, but potentially resolving with the things from earlier levels. After much search, very expensive search in this case, we would find a contradiction. In this proof, this gives a path which is 1, 2, 1 step, 2 steps, 3 steps, 4 steps in length. This is 1 step, 2 step, 3 steps, 4 steps, 5 steps in length. So a breadth first search would find a shorter solution in this case, in this particular example. But you can also use this in conjunction with depth first search. I won't go into much detail about this, but you can follow these slides through and you can get a sense of what a depth first search. Again, it's going to be a systematic search looking for all ways to resolve. It turns out that if you were to take a look at these 2 examples, you might be led to believe that always resolving what you've just found out with something else will get you a solution. It turns out that that's not always the case. In some settings, you might have a situation like this, and if you were to force yourself to resolve only with things in the last step, you might enter a repeating loop. So in this case, we get Q, we get P. This is a depth first search now. We get not Q. We continue resolving here. We get not P, and we start to cycle. You can create examples in which you've really got to resolve something. You might have to resolve several things on this path.